Okay, guys. So I am recording here, as you can see. I hope this time the recording is working. This is by far is the best software, Ink2Go. The university brought this software because we, as an instructor and students, have hard time with this type of WebEx stuff, recording our recitation in the lab and lectures. So, but this software by far is as you can see, is the best. So we talked about this. We try now those molecules, and before those molecules, you will see that the organic chemistry. We are still at the beginning of the course. The chapter 10 is just introduction for the whole course itself. So we have something called functional groups. As you can tell, functional groups, those are groups in organic chemistry, designate each class of organic chemistry. Now the OH here, hydroxy group, does designate an alcohol. So this is very important. This is an alcohol, correct? And this is another functional group. That's called halogen. Halogens. This is haloalkanes, called haloalkanes. This one here by itself, connected to carbon, that's called an aldehyde group. As you can see, those are functional groups, designates each class in organic chemistry, and each class has different physical and chemical properties and usage, application in a real life. So, and this one here, this group here, this is designated for amines. When I say amines is very large class and includes even amino acids. Amino acids, another word for it is proteins. When I talk about proteins, meaning what? Amino acids, which is really going to all our muscles, our body filled with this protein, amino acid, amines. And this is here, cyano group. This cyano group, this is an acid, hydrocyanic acid. This is the name of this one here, is called it's an acid, weak acid, hydrocyanic acid. It has a commercial name called blue acid. Blue acid, hydrocyanic acid. This couple drops of this can put a big body, such an elephant body, down within few minutes, couple minutes, 1 or 2 minutes. The whole big elephants, if you put something in the drink of that elephant will go down. So you heard about the cyanic acid, the cyanide, sodium cyanide, for example, is a huge, big, bad effect on it. So it's lethal. Sodium cyanide, potassium cyanide, all those, and hydrocyanic acid is a weak acid. Lethal, highly toxic, but it will connect itself to organic compounds, to alkanes and some other compounds, triple bond compounds, and it's precursor for, believe it or not, to organic dyes. Whenever you have nitrogen and carbon, that will give you a hint that you have organic dyes. You dye your hair, you dye your clothing, you dye whatever, make nice colors out of them. So that's the carbon-nitrogen connection. The second one here, that's an alkane, and it has a methyl group here. This is a methyl group. CH3 is a methyl. We'll come and look at those groups together. So this is a methane, CH4 is a methane, remember? this one here with the 4 here in hand, that's a methane. 4 methane. Now this methane, you can substitute for those hydrogens, whatever you like. So you can put amino group, take this one out. I'm taking this one here out, and put amino group. That will be amino methane, correct? I can put halogens, okay? Take, this is amino, called amino. The name of this will be amino, bless you. So amino, you start with the group. We start with the substitute group. You took from the methane 1 hydrogen, you replace it with amino group, this amino methane, correct? So you can replace this one here with the chlorine, correct? So you can, or replace this one here and take another one out. So then you'll say this is Cl, for example. Well, Cl the chloro starts with C, the amino with A. So the amino will win. Amino chloro methane. Amino A comes before C. You have to watch for what? You have to watch for the alphabets when you name. So amino chloro methane. The whole skeleton means the backbone of the molecule is a methane. Then you are starting substituting this methane hydrogens with other groups, amino group and halogen group. But you have to watch for the alphabets. A will come before B before C. So amino chloromethane. If you say chloroamino, that's not correct. That's wrong. Because C will not come before A. So the next one is aldehyde here. This aldehyde will be looking like this. H. This is an aldehyde group. Okay, that's H. That's formaldehyde. Formaldehyde. That's a common name. Formaldehyde. The real name we'll learn about the International Union for Pure and Applied Chemistry naming, nomenclature. That's this group here, Al. Start with Al. Like the hydroxy group with OL. This one here is carbon, that's eth. Ethanol. That's an alcohol. Eth, see? Eth. And then you end up with ANOL. That's an alcohol, ethanol. And this one here, because you have one carbon, correct? One carbon. I have one carbon here, one. So anytime I have one carbon will be what? Meth. So this is methanol. Methane, methanol here, Al. Meth is from the one carbon here. And then the ending Al. So meth, and then ending Al, methanol. What the name of this? Methanol. That's the real chemical naming. The commercial name is formaldehyde. The commercial name will come with the aldehyde or ketone, whatever the skeleton is. So the skeleton or the backbone of the molecule is an aldehyde. This is formaldehyde. Somebody will tell me where we use formaldehyde? Somebody take biology, NP biology? Somebody is taking biology classes? No? That's you preserve dead bodies. You have a cat there or frog, but you'll see them in a glass container. They put formaldehyde with alcohol with this compound here. So if I mix this and this, those two here, let me just make another color so you can recognize. If I mix this one here with this one here, I made a compound called formalin. Formalin is a mixture of alcohol and formaldehyde. Formaldehyde is the highest. It's about 80 to 90%. 10% is alcohol. And thus preserve the dead body. Whether you have a human dead body or a cat, or in the lab you have frogs cats, whatever that really is. And they preserve it because they keep the bacteria and all air filled with a lot of insects, a lot of bacteria. They keep them away. They cannot get in. If they get in, they will get dead. They will die. So that's the reason it's really called this preservative chemical mixture of formaldehyde and ethanol. I think we covered all of those. Let's take this one out. Everybody has this? You have the PowerPoints already posted for you guys. Let's take. This is the first one. It's a methane. So we have the one carbon. We'll go back and look at this. One carbon. It's the abbreviation of it is meth. Okay. And then 2 carbons, eth. 3 carbons, prop. We can go for until up to 10. 4, bute. Not but, bute. The U is pronounced differently from but it's bute. 5, bent. 6, hex. All those are Latin numbering. 7 carbons, hept. 8 carbon, oct. 9 non. Known, not none, known. Like bute is not but, known. And 10 is dec. You will see about 3 to 4 alphabets is the abbreviation. And then you can add the ending of the backbone or skeleton of the body. So this is meth. Since it's alkane, this is an alkane. Correct? So meth, and then we add to it ANE. That's a methane. And the methane has tetrahedral structure. Methane has what? Tetrahedral structure. The bond angle between here, hydrogen, carbon, hydrogen. What we said about this and those arrows. The dot arrows means the back of the molecule. That's a 3D, but I cannot have a 2D sheet and draw 3D. What I would do with it, I have to designate the front and the back and the top. So this is top, okay? This is back. This is up front, in front of me. So now I can visualize. If I have, we'll have an experiment. You will have an experiment in this in the lab. So that's a front. That's a side. That's a side here, side. So now you can. This way we can visualize a 3D structure or shape of a molecule in a 2D sheet. This sheet here, this screen is the 2D, correct? But with this type, the dot ones means always the back. And sticking out, that's front of me. Correct? And that is the top and this is the side, top and side. Okay, guys? They have just one single, there's no front and back. But I have to designate where is the back of the molecule, where is the front of the molecule is. Okay, guys, so we have all this one here, and then if I have an alkane, I have just to add ane to all of them, then I will get this an alkane. Decane. Decane means it's an alkane that has 10 carbons. Correct, guys? So, and the shape of alkanes are always tetrahedral. The shape is tetrahedral. And the bond angle is 109.5. Somebody heard about hybridization? I don't think so. You took the hybridization. Did you take hybridization in 1151? No, you did not. Well, what's happened is if you have like ethane, two carbons together, they will come and mix together. The hybrid in each of those, like ethane here, this is 3 here, and 3 in there. That's ethane, correct? Each one will mix with those two carbons, will mix with each other with the hybrid. So the hybrid means that's a mixture, combination of orbitals. So each carbon will come up with sp3. So now we have information about alkanes. Alkanes come tetrahedral geometry, molecular geometry tetrahedral. The bond angle between carbon, hydrogen in the back, or up front, or the sides, all those 109.5, 109.5. And the hybrid between the carbons, mixing carbons in alkane, is sp3. Is what? sp3. Means one orbital from the s orbital, and 1 electron resides in the s orbital, and the 3 is p3, 3 electrons in the b orbitals. Now, let me just remind you with this, and you tell me what the sb, of carbon. We have carbon. How many electrons carbon does it have there? What's the number of carbon? The atomic number? How much? 6. Okay, now, can I take this one out? Take this one out? So now, if this is 6, you did this one here, because I'm teaching 1151, I teach the other higher, 1211. So now, how we can accommodate 6 electrons, okay? But that's not valence electron. Valence electron is number of the group. Carbon, where is it? 4A. 4A. Carbon has 4 valence electrons. So we have to get all this, the sp electron configuration of carbon. So carbon will have maximum, 6. So 1s2. So the first orbital of carbon is 1s. Then you have 2s2. That's how many? 4. 2p, that's the second orbital, that's the first orbital. 2b what? 2. So if you add this, make what? 6 valence electron. You learned about this, I think you still remember it. So this is carbon. So where are the outermost shell? Well, the outermost shell is this. Second orbital. It has how many? 4. This and this. Those are the valence electrons. Electrons reside in the last or the outermost orbital, called valence electrons, and which is designated by the number of the group. Number of group is 4A, so, or 4, so valence electron will be what? 4. How about fluorine? What's the valence electrons of fluorine? Not the whole number of electrons, but what an atomic number. Atomic number is the whole number of electrons. But the valence electrons of fluorine, what do you think? Fluorine here. Correct. Fluorine in the 7 or 7A, in the old classical 7, in the 7th group. So fluorine has 7 valence electrons. How about argon? How many argon valence electrons? 8. Group number what? Argon is in group 8. So the valence electron will be as such, will be 8. So the number of valence electrons that are found in the last orbital, the last shell, represented by the number of the group. So 8, argon in the 8th group, so we have 8 valence electrons. That's just a review, will help us to understand the whole thing. So, can Can I take this one out? That's a methane. And we'll add to this another spot here, sp3 hybridization. Means each carbon, when connected to another carbon in alkane, it has to come up with each carbon, like an ethane here, 2 carbons. This one will be sp3, and this one sp3. So those 4 here, when the hybrid is, so will be S will have 1 instead of 2, and the P will have 3. See here? The 4. You add them up, still 4, but then you have 1 S, 1 electron in the S orbital, and the P will have, not 2, will have 3. So that's we call sp3 hybridization for alkane. So we don't have to know too much of this hybridization. That will go for higher chemistry. If you go higher chemistry, organic, you learn more of it. If you are interested, I will be more than happy to show you one-on-one in a meeting, if you can come to my office or to my WebEx office. So, office hours. So, let me take this one out. Functional group, we talked about functional group. Those are, they can halogens, nitrogen, oxygen, sulfur, whatever. So, characteristic of functional groups, as I said, those functional groups, they will give you, when it's attached to a skeleton. Skeleton means the backbone of the structure. The backbone of the structure, for example, is an alkane, A-N-E. So when you add those functional groups, they will give you different, no longer alkane per se, it's a compound with different physical and chemical properties. So it's still an alkane, but it's totally different from what you started with. Correct? Different. An example gave us to this. You have the CH4, that's a methane, and then you let it react with ammonia, for example. You get CH3 and NH2. So this is aminomethane. Aminomethane is totally different from whatever it started with. It's not per se a normal alkane. It's aminoalkane. It's not per se it's a normal alkane. It's aminoalkane. Are you following me here? So that's the case of functional groups. They have an effect to replace 1 or 2 or 3 of the hydrogens, correct? Of the alkanes to produce a new compound. Just to give you an example here, methane 4. Okay, so I'm replacing those 4 one at a time. So I replace one hydrogen. So I have CH3Cl. Replaced one of them. I can replace 2 CH2Cl2, replace 2 hydrogen. I can replace 3 CH3Cl. I can replace all of the hydrogen CCl4. So all those compounds, all the hydrogens of the methane are replaced one at a time, and I get totally different alkane characteristics. Correct? From one highly poisonous compound, this one here, CCl4, that's called tetrachloromethane. Tetrachloromethane, 4. Tetra means 4. Tetrachloromethane. That's highly poisonous, non-polar compound. Correct? This is methyl chloride, that's very active and polar. Then you have called dichloromethane or methylene chloride, dichloromethane. First is mono, we'll not say mono 1, but it's just chloromethane, dichloromethane, and this one here has CHCl3, trichloromethane. Trichloromethane, what's the commercial name of this? Somebody will know? CHCl3. So this one here, dichloro, goes in the polymerization, making plastic. This one here is a solvent. And the poisonous stuff, the tetrachloro, is a solvent. This one here, called chloroform. Did you hear about chloroform? Makes people asleep. It's in the movie. Put some in the piece of clothing and then put in the nose, and the person inhales this chloroform and get into sleep for a while. So that's the case. You can replace each atom of this alkane, okay, using those functional groups. So I'll take this one out. Everybody has it? Everybody has it, guys? Take it out. Okay, good, thank you. Taking this one out and then go further. This is types of functional group we talked about. So the hydroxyl group, this is brings you to just, I'm not going in detail, but at least the name of this hydroxyl group gives you alcohol, OL at the ending. This is an alcohol group.
Question.
Yes.
Could you zoom in a little bit?
Zoom a little bit. Okay. Let me see if it will allow me some. Hold on. Can you see it? Yeah. So sometimes it's just I have to deal with it. So let me. So the first one, the hydroxyl group, is meant to is meant as an alcohol. So whenever you have an addition like this group here, that will be an alcohol. That's by itself a group, a class of group, of organic group, totally different from alkanes. Alkanes are started here, yes, but stayed there. But now we have replacement one of hydrogen to get OH. Now we have a new class. Those are classes, organic class by itself. It has totally different physical and chemical properties. Not the same like the alkane we started with. Then you have a methyl group, correct? That can be another organic. That can be ethane, propane, whatever they are, might be. Methyl group is this. We have carbonyl group, and that will give us ketone. Ketone. This type of settings, double bond connected to two organic rest or substituent, that's we call it, are called a substituent or organic rest, the rest of the molecule organic. But this group here is functional group of a ketone. This functional group here is carboxylic acid. Now we are talking about class or classes here. Classes of organic. Totally different from whatever we started with. So this is carboxylic acid. Carboxylic acid. It's totally different from the inorganic acids. Correct? So carboxylic acid. C double bond OH. Then you have here what we call this one here. It's amino, but it's amines. That's an amine. This group here by itself is an amine. Now, can I take this one out? Go further? Because we have increased the whole thing. Can I take it out? Everybody has it? In the back here? Everybody has this? Okay, I'm taking this one out. And now we have the amine. Let's look at the at this group here. Now, what we can look at this group? We have phosphorus, correct? And we have 4 oxygen inside the phosphorus. That's a phosphate. Here it is. That's a group called phosphate. Believe it or not, phosphate is inorganic group, but it's attached to some organic compound. Correct, guys? Somebody will tell me what phosphate is used for. Phosphate, when it's attached to organic rest, organic skeleton, becomes very highly toxic compound, very highly toxic. I think part of the unexplosive, part of those phosphates are used in World War I, not II, but in World War I. As you know, phosphorus can burn, can catch fire. So, and this called what? Sulfhydryl, or we call them thiol. Thiol. Okay, those are just. We have plenty other functional group. Those examples of whatever we have. Okay, guys, those just brief examples or just small tiny examples of functional groups in the organic chemistry. So the last one, it has a sulfur and hydrogen. That's called thiol. Called what? Thiol. Or sulfur from sulfur, sulfhydryl. It has a hydrogen and the sulfur, so sulf from sulfur and hydrogen from hydrogen. Okay, guys, so I have to decrease it so we can. So that's a more functional group. As I said, that's just an example. And then we have ester group. The ester group can always ester is, as you will see later on, a combination of carboxylic acid and an alcohol. If I combine an alcohol, correct, with carboxylic acid, for example, this one here, if I have acetic acid, correct, COOH, that's for the acid, and bring ethanol to this, so now I'm getting out of this one here, CH3, COO, C2H5. So this is called ethyl acetate. Ethyl what? Acetate. Ethyl acetate is an ester. Ethyl acetate, for example. This is the same thing here. I put this an example here. It's a combination between alcohol and acetic acid. The acetic acid will have the backbone or the skeleton of the structure, and the alcohol will have itself at the end. I will start always naming them by the alcohol. So ethanol, so ethyl acetate. Amines, we talked about amine group, correct? That's a methane, and amine, that's aminomethane. This what? Amino group, aminomethane. Why methane? One carbon. If we have two carbons, will be aminoethane, correct? If we have three carbons, then we have a problem. Why? Because you have to locate where the amino group is connected to. Are you following me here? So with the amine groups, we have a problem is when you have more than one carbon, then you have to designate a number for these amino groups. The rest are just hydrogen, the rest of this hydrogen. So you will say always the least numbering, always the least numbering. That's your goal. I say this is 1, this is 2. Or I can go from left to right or right to left. This is 2. So this is now 2-aminopropane, 3 carbons, all of the rest of hydrogens, all the rest is hydrogens, hydrogen, hydrogen, and the rest is hydrogen here, and hydrogen here. So this is 2-aminopropane. So the skeleton or the main structure is made of 3 carbons. The second carbon of this skeleton or this backbone of the structure, we have amino group connected to. So then you have to designate the location of amino. Where is it? Is it in the first or the second? No, that's the second. So this will be 2-aminopropane. 2-aminopropane. The imide coming from the amines. The imide's like an ester, correct? So the imides is let me take this one here first, then we'll go for imide and thiol. Thiol, we talked about thiol with the sulfur. Can I take this one out? Everybody has it? If you don't have it, please let me know. I'll wait. So let's take this one out and let's look at the imides. The amine is straightforward, correct? It's amino group, but then sometimes you have this this amine group, whatever the amine group here, and in this they have a keto group, double bond here, and this is R. This type of structure here, okay, this type of structure, carbon, nitrogen, and then the oxygen is a double bonded to the carbon. This is called an imide. And your feeling will tell you that's like an amine is a base, correct? Amine is a base, and this coming from can be from an acid, correct? So it's like a neutralization type of setup, an imide. It's a salt. You get it's a salt, and it can be a salt, an imide. So that's the case here. R can be any substituent here. So that's an amine, N, nitrogen connected to carbon, and carbon connected to double bond. That's an imide. Okay. An imide is not very active like an amine, correct? It's not like an amine. Amine is more active than reactive. Then you have a thiol. Thiol is sulfur and hydrogen. Sulfur and hydrogen makes thiol, or sulfhydryl or thiol. So you have here, you have a sulfur here, you have a hydrogen. And the name of this now will be thiol, not sulfhydryl. No, that will be that's a methane. One carbon, correct? One carbon connected to the CH group, thiol. That will be what? What will be? The structure is the structure is methane. You can relate the whole thing to methane. So it has two. So we can call this one here a thiomethane or methyl thiol. We can say the best is this is a methyl group now, methyl thiol, because the methane is not a group. It's not an alkane, but connected to the main functional group. CH is a functional group called thiol. So we can call it methyl thiol. Methyl thiol. Okay, guys? So let's take this one out. That's the last chapter of chapter 10, isomers. Isomerism is type of chemical compound or organic compound that they have the condition for this. They have the same two conditions. Those conditions is they have the same molecular what? Mass. So same first molecular what? Molecular mass. And same number of carbons, same of atoms. Sorry, not carbons, but they have carbons, of course, of atoms. So those are organic. What they are differ in? They are differ into something called arrangement in space. When you start arranging the shape of this molecule in space, then you create identical compound, but the arrangement in space is totally different, correct? So, arrangement in space, arrangement in space is different. So now we have constitutional isomers and we have stereoisomers. The stereoisomers are enantiomers and diastereomers. So enantiomers means they are mirror image. If I put a mirror here in between, let's look here. If I put a mirror here, see here, see, they are mirror image to each other. Those two molecules, if I put one molecule shape of it inside the mirror, I get the other one. When they are together, they are enantiomers. We call them what? Enantiomers. Now the diisomer or diastereoisomers, those are not the same molecule, but they are not mirror image to each other. That's the difference between them. The same molecule numbers, the same number of atoms, how many you can count, how many hydrogens, how many carbons, how many chlorine. The same molecule number of molecules, the same molar mass. But the arrangement in space is totally different. Correct? So now, with this is not mirror image to each other. And you can see, because they are not mirror image to each other, I can take this out, show you just, that's arrangement in space stays there. But if I put a mirror here, are they mirror image to each other? No, they are not mirror image to each other. That's the key. We have one is called enantiomer, one called non-enantiomer or diastereoisomers. Enantiomer, non-enantiomer, or we call them dia, these two together, stereoisomers. So meaning we have out of them two types, especially if you have a double bond, the specific with double bonds. This is specific of single bond, by the way. So mirror image is happening whenever you have single bonds, correct? Bonds. Here, this stereoisomers always characteristic with double bonds. So that's a very crucial difference between them together. The mirror image are always always single bonded molecules. Put them in the mirror, they will switch, but they are mirror image to each other. However, the stereoisomers, they are mirror not equal. They are not mirror. They don't have a mirror image to each other. They have the cis means the group, the rest or the substituent or the group here. Like for example, here is a methyl, correct, and a methyl. So they are in the same level, the same plane. Those are cis. Cis means like coming from sisters. So those are sisters, neighbors to each other. They are relevant to each other in the same plane. If they are the opposite to each other, like we have here, they are trans. Trans means opposite. Cis means in Latin together, and trans means the opposite. Are you following me here? So that's the trans is the substituent, organic substituent can be R, not the methyl group, can be any R. If those two R's are opposite to each other, that's a trans. If they are in the same plane, they are cis. Now, they have to have, cis are always related to what? Double bond. You cannot have single bond cis and trans. Are you following me here? Because then you'll be trapped into image, mirror image to each other. This one is a mirror. Put a mirror in between, you see the other one inside the mirror. One's outside the mirror, one's inside the mirror. But here you can put a mirror, you will not find them together. You see? Here is they are different. Instead of methyl group inside the mirror, you will see hydrogen. Or you see another group. So they are not mirror. So it's not, so this one here, not mirror image. not mirror image to each other, not mirror image. Okay, so the constitutional, that's stereoism. We talked about this. The constitutional is how you look at the whole compound where is found, correct? So for example, you have here, let me give you an example here. For example, I have here, I put chlorine 4. That's alkane. That's chlorobutane, correct? 4 means butane. Then I can put chlorine can be chlorine can be here, but sometimes the chlorine can be where? Not here, but you take the chlorine is now in the first one here. Chlorine is here instead of here. Here is hydrogen, but chlorine is here. Those type of the molecule, the substance when it's moving at different atoms, that's we'll call them the constitutional structure. It's the same atom, but the substituent is changing position among the carbon atoms, correct? This one will be, this name here, the first one will be 1-chlorobutane. This is here will be 2, that's from here to 2-chlorobutane if I put the chloro here, correct? If I put the chloro in the second, it will be 2-chlorobutane. So 1-chlorobutane and then 2-chlorobutane looks are almost identical in molecular mass. However, the physical properties and the chemical properties might differ a little bit. Not the same compound. That's what it says. Not the same compound. So the isomers, because of the arrangement of the atoms inside the space, they will give rise to a problem for us because they will change their physical and chemical properties a little bit. Not the same. Not always the same. So then we have here part of the stereoisomers. We have rotamers and conformers. So, well, what's the difference between this? Rotamers is really a conformers. Conformers means you have the ability, correct, especially in amino acid and amines, the ability of the atom the carbon atom to rotate among themselves. If I have 2 carbons together here, 1 carbon here, 1 carbon here. So if I can twist them here like this, what will happen, whatever attachment on this now is down, on this will be up. So if chlorine is attached there, chlorine will be at the bottom, and chlorine at the top, because I moved one, I twist, I rotate, correct? That's only can happen in what? In single bond. Again, see here? Guys, only. The same thing here, and those cases only. If I have a single bond in a compound in alkanes, for example, single bond in alkanes, of course, not double bond, then there is no restriction for the rotation of the carbon atom. The carbon atom single bond can rotate easily. Now, this problem is not the case if I have a double or triple bond. You cannot rotate double bond. You will break them. Triple bond, almost impossible. They are short in distance between the carbon-carbon triple bond, very short, and you cannot rotate them. The only you can rotate the carbon-carbon single bond. So single bond, they can have mirror image, correct? And they can rotate among themselves. So the rotation is making rotaisomers, or rotoformers, correct? So this is the big name of it, correct? That's the big name of it, well, meaning the ability to to twist or to rotate between carbon atoms within a single bond. Double bond is difficult, almost impossible. Triple bond, forget about it. It's very short. You cannot rotate those. Okay, guys? Any questions so far? Any question? Okay, so that will conclude chapter 10. Somebody was asking why we are taking chapter 10. Well, we have to, because the idea is we are looking for introduction, and all what we have taken so far is an introduction. Now we are going for real stuff. We have a couple minutes. At least we can start with it. Hydrocarbons. We talked about this is that's the first one. Hold on. Chapter 11. Okay. I'm not going through the whole thing, but next when we meet, we'll go through this, I think Thursday. But we talked about the alkanes being, in general, not polar. The hybridization is sp3. The geometry is tetrahedral, correct? And they have alkanes. They have a double, single bond. Now the main formula is, I'll stop here, is carbon N, and H is 2N plus 2. So if carbon is 2, then hydrogen will be 2N, 2 multiplied by 2, N is 2 here, correct? An example. Plus 2. So this one here will be C2H, this is 4, plus 2 is 6. So we can see the general formula for alkanes. Now, that's the alkane formula. I'll stop here because I want to upload this. The alkenes, on the other hand, the alkenes, double bond, ENES, double bond, then they have a formula different, CNH2N. Okay, guys? And the alkyne, the triple bond, we'll come back and look at this, CNH2N minus 2. So we'll come back and look into this in general. I'll stop here. I'll stop recording. I will see you in Thursday. This time it's working. Next time we'll not have technical properties, I hope. Okay, guys? And I will record for you the rest of the beginning of chapter 10.